Okay, so let's start our lecture today. So, uh, okay, so, uh, okay, so last time we showed that, um, uh, yeah, so last time we showed that there is an antiguity zeta z of the Weierstrass polynomial to be 1 plus z plus summation of omega not equal to 0 of 1 over z minus omega plus 1 over omega plus z over omega cubed. Okay, sorry, omega squared. And we show that it's an out function. Okay. And then okay, and so then it says that the convergence is obvious. Okay, for apart from the term 1 over z. Over z, we obtain the new series by integration from 0 to z. Along any path. Any path through the poles. Okay, any path that does not pass through the poles. Okay, so apart from the term over z, we obtain the new series by integration. Okay. We obtain the new series from the pass through the poles. So here, integral from 0 to z. Okay. We ask the AI about this one. So, so for the okay, so for the expression of zeta z, we have that it is given by 1 over z plus summation omega not equal to 0, 1 over z minus omega plus 1 over omega plus z over omega squared. We want to show the convergence of this series. Okay, so in the book he writes that the convergence is obvious apart from the term, because apart from the term 1 over z, we obtain the new series by integration from 0 to z along any path that does not pass through the poles. Okay, so okay. I don't understand why it is obvious that we can obtain the new series by integrating from 0 to z along any path. Yeah. What theorem can we use to prove this fact? Okay, still thinking. So okay, so he is saying that so we take one summand of this Weierstrass polynomial. Okay, so the Weierstrass polynomial is equal to z plus summation omega not equal to 0. Wait, 1 over d squared, right? Wait, I was a little bit confused. So yeah, so this PZ is 1 over d squared, yes. Take the sum over 1 over z minus omega squared minus 1 over omega squared. Okay, so the idea is that, okay, so we take one summand of negative t, which is okay, so we take one summand of negative p, okay. So which is equal to negative yeah. One over d minus omega squared minus 1 over omega squared. Okay. So we know that the integral of this one, okay. The integral of this one is equal to 1 over so take the integration. Which is equal to exactly the yeah, z minus omega plus z over omega squared plus c. Okay. So okay, so okay, so this is not exactly true. Okay, so what I mean is that yeah, so if you integrate this guy from 0 to z, okay, so let's call this variable zeta, okay. So forgive me that I abuse the notation by a little. So, and then it is this guy, but when this data evaluated at z and at 0. Okay. So okay, so then if you plug in, right? So if you plug in, it will be the 1 over z minus omega plus z over omega squared, and then minus become plus 1 over omega. Okay. Oh. Okay. Yeah. So this is exactly one term, which is inside zeta z. Okay. And for the principal part at 0, what do you mean by principal part at 0? Oh, I see. So, okay. So this is a non-principal part. We take the integral, we get that. Okay. So for the principal part, okay. So remember that principal part is just the negative 1 over z squared, right? Take the integral, which is equal to 1 over zeta. Okay, I think here we should take a limit or something. Maybe you want to use some some improper integral. Okay, so let's forget about this case right now. Okay. Okay. Okay, so let me ask you again question. So, okay, so when you write the integral from 1 over z minus p of zeta d zeta, which is equal to integral from 0 to z, integral from 0 to z minus 1 over zeta squared plus summation omega not equal to 0 minus 1 over theta minus omega square minus 1 over omega square d theta. So what guarantees the convergence of the integral? Because you have a pole at 0. So is there any theorem you use for the, because yeah, so again, right, so I think in a previous argument you said that if the integral from 1 over z negative 1 over theta squared d theta is equal to 1 over z. So up to the expect issue that, okay, up to the expect issue that the lower endpoint 0 is a pole, right? So what happens if yeah, so I know that. So basically, I know that. Yeah, so for the other part, I don't think there's an issue, right? So you can freely, yeah. So basically for the yeah. So for the other part. Yeah, so for the other part, I don't think there is an issue. But for the principal part, I don't think you can integrate from 0 to z for the principal part. So how would you handle the principal part? Right. So if you do like the integral from 0 to z of the rest part, I know that the rest part will definitely converge for the integral, because yeah, we know that it will converge for the integral, if the path is doesn't hit, right? So how would you guarantee that? Because since you are using the p, so the rest part is being derived from wait. So is the rest part also converges? Yeah, so the rest part is also a well-defined. Oh, so the rest part is also a well-defined sequence, right? So each point, the value, because we know that PZ, yeah, of course we show that the convergence of the rest part, right? So because the rest part is just it converges at any point. Yeah. So and then basically you can take the integral, right? And then okay. Oh, this is a finite value. This integral is a finite value, right? So what you do is that, okay, it makes sense. So yeah, so you get, yeah, so this give you what? This give you exactly this guy. Okay, this give you exactly this guy. Okay. Oh. Okay. And then you plus 1 over z. Yeah, and then you just add 1 over z. Okay. Okay, so it will converge. Okay, it will converge. Okay. Okay, so that shows the property of the convergence. Okay. Okay, so okay. Yeah, I can do it without. Yeah. Okay. Okay. So okay. Okay, so okay, so it is clear that this theta z satisfies conditions zetas of z plus omega 1, which is equal to zeta z plus eta 1. And okay. Okay, so zeta of z plus omega 2, which is equal to zeta z plus eta 2, where eta 1 and eta 2 are constants. Okay. Okay, let's see why these are constant. Okay, so if you okay, let's see what happened here. So if you okay, so if you let's see so if you put, let's say, z plus omega 1 okay, so 1 over z plus omega 1. So you wanna compare with the original zeta z, okay? Then plus summation omega not equal to 0. Okay, so again, okay, I think there is no difference for this term. Wait, I think there might be a difference because this omega can be equal to 0, right? Right. So, okay. So here you are taking over all the like n1, n2. Okay. Not equal to 0. Okay. And then here, you are taking. Yeah. So think about like the terms. So theta z, right? Okay, theta z. Think of the term that so this is over all. So the term being subtracted is ranges over all the n1, n2. Okay. So here, if you do the same thing, but add another, wait. So here, you can say that minus this omega plus omega 1. Sorry, minus omega 1. Okay. So, so then it becomes, if you minus 1, it becomes 1 plus minus 1 and 2 not equal to 0. No. Negative 1, 0. Okay. Okay. So, yeah. Okay. Okay, so here we can break it up, right? Shoot. So I think we get an actual omega 1 over omega squared. Okay. Okay, let's see what is the real difference between these two. Okay, so definitely there's a difference between the first two terms, right? And then for the second term, okay, let's say that you subtract this from that, okay. So then it will becomes 1 over, so maybe I write this. Minus z to z. Okay. So which is equal to, so for the first term you get z plus omega 1 minus 1 over z. Okay. And then for the second term, okay, so what is the term that it has but it does not have? So okay, I think the thing it has is it has 0, 0, right? So basically, shoot, I think I forgot no, I didn't. Okay. Yeah, so it has a 1 over z. Right, it has a 1 over z here. But it does not have negative 1, 0. Yeah, negative 1, 0 is the thing that it does not have. So minus. So 1 over z minus omega 1, I think. No, I don't think so. It should be 1 over z plus omega 1. Okay. Because I'm using the, yeah, I'm using these coordinates for the minus the situation. Okay, so these are the coefficients for this guy. Okay, so these are the coefficients for this guy. So this guy cannot be negative 1, 0, right? So namely, I want to have the, okay, but in this case, this can be negative 1, 0, right? So there's an extra negative 1, 0 here. Okay, so minus negative 1, which is okay plus omega 1. Okay. Yeah, because so this just becomes negative 1 times omega 1, and this is 0. Okay. And then you take this. This is the one that this one does not have. So you take this one minus this one. Okay. Oh, you see that this cancels out. Okay. So then I think everything else follows the same, right? And then it just becomes omega 1 over omega squared. Oh, sorry, take the sum. Okay. Plus, we take the sum over omega not equal to 0. Okay. I think by an estimate, this one definitely converges. So, oh, sorry. So what estimate do we use here? I think there's an estimate that's we discussed earlier, right? So there's an estimate. Let me think. Yeah, so why this one converges? That's the question. Does this has some cancellation? I would suspect that it has some cancellation. So if we have a, let's say, 1 omega 1 wait, can we use the same argument? No. Can we take a sequence of, wait, we can't, right? We must take the derivative. Oh. Yeah, so why it is converges, this one? so let's try this. So let's take the square of this one. Okay. Let's see if there is some feature that allows us to do some calculation here. Okay, so okay, so if we have n1 omega 1 minus n2 omega 2, okay, let's see what happens. So with the same thing, right? Okay. Oh. No. Plus, sorry, this is called minus 2n1 n2 omega 1 omega 2 plus n2 squared omega 2 squared. And then yeah, so same thing for the like n2 omega 2 minus n1 omega, like minus n1 omega 1 plus n2 omega 2. So it's the same thing. Okay. And then the last one will be minus omega 1 omega 2 minus omega n2 omega 2, okay, square, which is exactly the same as this one. Okay. So when we add them all up, they should become wait, we can't really add them, right? Yes. That's the question. So yeah, so we are not really adding them because they are in the denominator. Yeah, so why? Can we think of the idea of ribbon socks? Like the you take the function. Okay, you take the function. Okay, you basically the idea is you take away the origin as squared, and then you do the integral 1 over x squared. Is it converge or not? I'm not sure. So yeah, so let's say you use a polar coordinates. R cosine theta squared R d theta. Okay. And then R goes from, let's say, 1 to infinity. Theta goes from 0 to 2 pi. Does the integral exist? let's see. So maybe you want to do a U stop, right? Wait. Is it filmed? Okay, it is filmed. Okay, good. So okay, so okay, let's take the inner interval first. See if we converge or not. So maybe just the R first. Okay, so we plug in one over u cosine squared theta, like a 1/2, right? Oh, okay. It diverges. Okay, so oh, I see it. I see why it diverges, because simply just okay, cancel this one. Okay. Okay, so oh. But you are integrating over cosine theta, right? Does that make a difference? I don't think that makes a difference, because integrating cosine theta basically just like wait. Okay, so that's the point. Wait. Does that make a difference here? Oh, I'm not so sure actually. So, okay, let's see. So, what happens if you take the integral of theta first, and then do the integral over the radius? Can you do the antiderivative with respect to the theta? But even though you get a finite number out of the thetas, you still wait. You still have to integrate 1 over r, right? Because yeah, you still have to integrate 1 over r of some constant number. Which falls apart. Ah, okay. 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 So let me get back to next time. Okay. Let me get back to this next time.